Welcome to the Deep Dive. We've been looking at your questions, and today, well, we're tackling the t-distribution.
That's right.
Our mission here is pretty straightforward. To give you a solid grip on when you should use it, why it's important, especially when you're maybe dealing with less data than you'd like.
Yeah, absolutely. Because the t-distribution, it really shines, you could say, when we're in a situation where we don't know the population standard deviation.
Which happens a lot, right, with smaller samples.
Exactly. It happens all the time. And instead of just, plugging in an estimate and hoping for the best, the t-distribution is specifically designed to account for that extra uncertainty, the uncertainty that comes from having less information to work with.
Okay, so it's almost like the normal distribution assumes you kind of know everything perfectly. And the t-distribution is a bit more, let's say, grounded in reality when our data isn't quite so complete.
That's a really good analogy, actually.
Yeah.
And you see that groundedness in its shape. The t-distribution famously has heavier tails.
Heavier tails, right.
Which just means, compared to a normal distribution, it assigns a bit more probability to values that are far away from the mean. It acknowledges that with less data, you're just more likely to stumble upon surprisingly high or low values.
Okay, that makes sense. So what happens then as we, get more data? Does it change?
It does significantly. As
Yeah.
your sample size increases, something called the degrees of freedom also increases. Think of degrees of freedom as basically your sample size minus 1. It's a measure of how much information you have.
Gotcha. Sample size minus 1.
Yep. And as those degrees of freedom go up, the shape of the t-distribution changes. It gets tighter, those heavy tails slim down, and it starts to look more and more like
The normal distribution.
exactly. It converges towards the standard normal distribution. That initial uncertainty we talked about, it kind of melts away as you gather more evidence.
Right. Fewer data points mean more potential wiggle room for the real population value to be different from what our small sample shows. So using the t-distribution is critical then for making, trustworthy conclusions from smaller data sets.
Absolutely critical. If you have a small sample and you just use the normal distribution anyway, you risk being overconfident. You might think your results are more precise than they really are. The t-distribution gives you a more, honest assessment of the uncertainty.
Okay. Now, we also got questions about different types of t-tests. People mentioned pooled versus Welch's. What's the story there?
Good question. It really comes down to one key assumption. Do the two groups you're comparing have the same variance, equal spread in their data?
Okay.
A pooled t-test assumes they do. It sort of averages the variance from both groups together. Welch's t-test, on the other hand, doesn't make that assumption.
So Welch's is maybe safer if you're not sure about the variances being equal.
Generally, yes. It's more robust, more reliable when the variances might be different. Many statisticians actually recommend defaulting to Welch's test nowadays.
Interesting. So apart from the variance assumption in the pool test, what are the fundamental requirements for using t-tests in general? What needs to be true about our data?
Well, the big ones are independence. Your data points shouldn't influence each other.
Right.
And the data within each group should be at least approximately normally distributed.
Approximately. So it doesn't have to be perfect.
No, not perfect. The t-test is fairly robust, meaning it can handle some deviation from normality, especially if your sample sizes are reasonably large. But, if your data is wildly non-normal, especially with small samples, then the results might not be reliable.
Okay. And let's say we run the test. How do we use the t-distribution to actually make a decision? Someone asked about interpreting critical values.
Right. So you calculate a t-statistic from your sample data that basically measures how far your sample result is from the null hypothesis in terms of standard errors. Then you compare that calculated t-statistic to a critical value. You find this critical value in a t-distribution table, or more likely, from software. It depends on your chosen significance level, your alpha often 0.05, and your degrees of freedom.
And if our calculated value is bigger than the critical value.
If your t-statistic is more extreme, either larger positive or smaller negative than the critical values, it falls into the rejection region. That means your result is unlikely enough under the null hypothesis that you reject it.
So the critical value kind of sets the bar based on the t-distribution's shape for that specific degrees of freedom. For what counts as surprising enough.
Yeah.
We also had a question about regression analysis. Does the t-distribution show up there too?
It certainly does. In linear regression, when you estimate the slope coefficient for a predictor variable, how much the outcome changes for a one-unit change in the predictor, you get a standard error for that estimate too. To test if that slope is statistically significantly different from zero, you calculate a t-statistic, the estimated slope divided by its standard error. And then you use the t-distribution, again based on degrees of freedom related to the model, to see if that coefficient is significant.
Wow. Okay, so it's quite versatile. One last thing. What if the data really isn't normal? You mentioned robustness, but what if it's like really skewed?
Yeah, if you have strong non-normality, particularly with smaller samples, the p-values from the t-test might not be accurate. In those cases, you might look into non-parametric tests like the Mann-Whitney U-test instead of an independent samples t-test because they don't assume normality. Or sometimes transforming the data first might help.
Good alternatives to keep in mind. Okay, so let's wrap this up. The key takeaway seems to be key distribution is your friend for smaller samples when you don't know the population variability.
Definitely. And understanding degrees of freedom is crucial for using it right.
And remember those assumptions, independence and approximate normality. Be aware of them.
Exactly. It's all about having the right tool for the uncertainty you face.
So here's a final thought to leave you with. We live in an era of exploding data volumes, right? Big data. As data sets get absolutely massive, the sample standard deviation becomes a very, very good estimate of the population standard deviation. And the t-distribution looks almost identical to the normal distribution anyway. So will the t-distribution become perhaps less critical, maybe even a bit obsolete in certain fields dominated by huge data sets? Something to ponder. Thanks for diving deep with us today.